Hello, I'm Ezra. This is AP Calculus AB and BC Review, Unit 1, Limits and Continuity. In this unit, we look at how we define and solve limits. We look at continuity and discontinuities, as well as how we prove it with limits. We look at what happens when limits go towards infinity, and finally we look at intermediate value theorem. So, let's get started. So what is a limit? Well, a limit is when you have your variable, x, go towards a certain constant in a function. So if you take a very simple function, like f of x equals 2x, as x approaches the number c, well, there's nothing special about this function. You can just plug c directly into here. We'll have 2 times c. If you have limit as x approaches 4, for example, well, as x approaches 4, for the function 2x, you just have 2 times 4, which is going to be 8. However, limits become important when we look at functions that are not nice and even, nice and normal, like 2x. So first, we're going to look at what that looks like on a graph. So over here, we have some arbitrary function with a hole at x equals 3. So if you try to look at the limit as x approaches 3, right? You can't just plug 3 into the function this time. If you plugged 3 in, you wouldn't get anything. There's a hole there. So what you'd have to do is look at it as it approaches from the left and from the right. So right here, we can just say that this value is 4, for example. And if we look at the graph, we can see that as it goes towards this point, it goes towards 4 from the left and 4 from the right. So we can say that this limit equals 4. However, if this function, let's say, went like this, right? And you had another hole here. Now, when you look at them from different sides, you'd have x equals 4 on this side, or y equals 4 on this side. But then when you look at it coming from the right, y equals 6. So the limit here wouldn't exist. And that is the definition for when a limit exists. So a limit only exists if when you approached a number from the left side, which is what this minus denotes, it equals the limit as you approach x from the right side. So on any graph, even if it is defined at that point, so let's say this is x equals 4, x equals 4 is defined at y equals 2 here. But since traveling from the left and traveling from the right, you approach a different value from each time, then the limit here does not exist. So if you were asked this on a question, you would say the limit is non-existent. You can also look at this in a table. So any arbitrary table that it can give you usually will be set up something like this. you have a number in the middle. This would be what the limit is approaching right here. So in this case, it's as x approaches 2. And then you would have numbers that are getting closer and closer to that number on both sides. Now, what really matters is this y value over here. So if this were a normal function, you could say that this gives you 3.9, this gives you 3.99, this gives you 4, then 3.99, for instance, if it were, you know, a quadratic, right? This is something you would see most of the time when looking at a function. However, if you had dne here, right? And then the same thing, 3.99, 3.9, then even though at x equals 2, the function's undefined, you can see that even from the left and from the right, it approaches the same value, which is going to be 4. So you can say the limit as it approaches 2 is 4. However, if I were to, for instance, change these numbers to 6, well, suddenly this limit is not approaching 4. This limit's approaching 7. This limit is not going to exist. And it's the same concept even if 2 is defined, and even if 2 is connected to one of the sides. 2 is 4 here. This function would just look like, you know, something like this. And then up here is the 7 that's approaching from the right side. So it's defined at 4, and it even approaches 4 from the left side. From the right, it does not. It approaches 7, so this does not exist. Algebraically, you can also solve limits in things like rational functions. So, for instance, if I have x squared minus 5x plus 6 over x minus 2, right? Limit as x approaches 2 in this, what would it be? Well, let's plug 2 in. 4 squared minus 20 plus 6, not minus 20, minus 10 plus 6. Okay. And then x minus 2 on the bottom is 2 minus 2. So 2 squared is 4. 4 plus 6 is 10 minus 10 is 0. So this top is going to be 0. And then the bottom, 2 minus 2, obviously 0. So then this is going to be 0 over 0. Does not exist. However, these can be factored into x minus 2, x minus 3, and then x minus 2. And now we can take out that denominator, and this is x minus 3. So this expression is essentially equivalent to the limit. Well, I guess I can't erase that. It's equivalent to the limit as x approaches 2 of x minus 3. Which, now, we can just plug 2 in, direct substitution, which will give you negative 5. So this would be your answer for a problem like this. Finally, we can evaluate limits of composite functions. So I'm going to give 2 graphs here. I'm going to give g of x, which I'm always going to change, or this is the one that I'm going to be changing. And then this is going to be f of x. So I'll label it so it's easy for you to see. Now, if I said the limit as x approaches 3 of f of g of x, here we can directly substitute this into g, this x equals 3, and g of 3 here, we've defined it as 4. So this is just the limit as x approaches 4 of f of x. Now, if we look at f of x, the limit as x approaches 4 of f of x is undefined. This function, from the left, you approach a value, let's just say 6, and then from the right, you approach -3. So if you were given these two functions on an MCQ, and it asked you what the limit was as it approaches 3, it's going to be undefined. And that goes for even if it says, what is the limit as it approaches 3 from the left or from the right? Because if you look at g, both sides, it's approaching the limit from the same to the same point. So it doesn't matter, because once this gets plugged into here, that plus or minus goes away. However, let's say g of x was not this nice, beautiful curve. And let's say it had a bump at x equals 3, right? And this is 4. Now, if I do the limit as x approaches 3 of f of g of x, that is not what I meant, then you might think that it's still 4. You just plug 4 into here, and then you end up getting undefined. But because when you approach the limit from both sides, this is important. So if you approach it from both sides, coming from the same direction, so from here we're going from down to up, down to up. When you plug this 3 into here, you have to change, or I should say add a direction to the limit. So because they're coming from up on both sides, instead of you putting the limit as it approaches 4 of f of x, you do it as it approaches 4 from the left, negative. Because it approaches, you can think about it coming from negative to positive. And now here, it approaches 4 from the left of f of x. That's 6. This is defined. And if I gave you a function like from some sort of absolute value function, right? Or I should fix this and make it up here. This is unrealistic, but here it's coming from top down on both sides. So, as you can imagine, f of g of x, you have this 4 that it approaches from top down on both sides. You do the limit as it approaches 4 from the right of f of x. And in which case, this would be -3. So don't get tripped up on this one. you might think that it doesn't exist because f of 4, the limit of f of 4 doesn't exist. But if they come from the same side, look at which side both of them come from, and then if it comes from top down, it's negative, and it comes from, or if it comes from down to up, it's negative, and it comes from top down, it's positive. Next, we're going to look at the types of discontinuities. So you really have three main ones. And while they're all discontinuities, they have different properties. So we have holes, jumps, and asymptotes. A hole we've looked at before. This would be in something like x minus 2, x minus 3 over x minus 2. When you plug 2 in, it doesn't exist. But you can remove the 2. That's why a hole is also called a removable discontinuity. When you remove the 2, you can then still take the limit of it. Jumps and asymptotes are non-removable. Jumps often look like this. You can have one open circle or two open circles, but you cannot have two closed circles because then that wouldn't be a function. These are non-removable, and you can never take the limit. Here, if you have a hole, you can always take the limit. Asymptotes, these are not removable either. However, these depend. I'll write that a little closer. They depend, and what do I mean by that? In this case, if you wanted to take the limit as x approached 0, you go from the left, you hit negative infinity. You go from the right, you hit positive infinity. That's not going to work. However, if I had a function such as this, which you could model this as 1 over x squared, right? Then, if I go from the left, I hit infinity, and if I go from the right, I hit infinity. So even though it is a vertical asymptote, you can still take the limit as x approaches 0. As long as the rule is satisfied, that is the same from the left and the right, you can take the limit. Here, it will always be satisfied. Here, it will never be satisfied. And then here, depends on the direction of the asymptote. That is the main takeaway from these discontinuities. Now, it will very often ask you to prove continuity on a certain interval. And this is very easy. So, it will pretty much always be given to you as a piecewise function. So if, for instance, I have 1/2 x cubed plus 1 for x is less than 2. And then I have negative x plus 7 for x is greater than or equal to 2. Now, it would ask, is x continuous, or is f of x continuous at x equals 2? It might ask this in different words, like can this theorem be used or this theorem, which we'll go into later. But in simple terms, is f of x continuous at x equals 2? All you have to do is take 2 and then plug it in to your function from both the left and the right. Essentially, you take the limit. So as x approaches 2, from the left, you're going to get 1/2 2 cubed plus 1, which equals 5. The limit as x approaches 2 from the right is -2 plus 7, which also equals 5. So, since these limits are equal, and f of 2 equals 5, this is the important part. F of 2, which would be this, because it says x is less than or equal to 2, so equals x equals 2, f of 2 equals 5. Because these are all equal, that means it is continuous at x equals 2. So that is the important rule. The limit must exist at the point. So that means from the left, it equals, from the right, it equals, but with the added condition that f of c must also be equal to the limit. So if I take that same function with the 1/2 x cubed plus 1 as x is less than 2, and then the -x plus 7 as x, instead of greater than or equal to, I'm going to say x is greater than 2, and then I define the function as 9 at x equals 2. Because of this, the function is not continuous, because as we proved before, this limit equals 5, this limit equals 5, but now we've added this extra condition, f of 2 equals 9, and this does not equal the limit, so this is not continuous. They also will sometimes ask you to find a variable that satisfies continuity. So, if you have f of x equals 2x plus k, and then kx squared minus 5, and then we're saying x is less than 2, x is greater than or equal to 2. Now here, first, you want to set them equal to each other, because remember, both of these sides will have to equal each other at x equals 2 for this to work. Second, plug in your 2 for x. This is the x value it has to equal at. So if you plug in 2 for both x values, you'll get 4k minus 5 equals 4 plus k. Now, with simple algebra, move the k over, move the 5 over, you get 3k equals 9, and thus k equals 3. So, taking k equals 3 into the equation, we plug it back into this equation. So, instead of kx squared, we'll have 3x squared. Instead of 2x plus k, we'll have 2x plus 3. Now, we can do the same process we did before to figure out if this is continuous. So, let's try it. Limit as it approaches it from the left is going to be 2 times 2 plus 3, which is going to equal to 7. Limit as it approaches it from the right, 3 times 2 squared, which is 4, minus 5, which equals 7. And then since x is greater than or equal to 2 at this point, it's going to be the same thing for f of 2. F of 2 will also equal 7. Thus, it is continuous here. This is a very common problem to be asked on the test. Second to last topic in this unit is going to be limits as they go to infinity. So, as x approaches infinity, or it might be worded as x increases unboundedly, so and so, we'll take some function, 1 over x. So if you look at the graph of 1 over x, you don't have to do any math to realize that as x approaches infinity, it's going to be 0, which makes sense. 1 over 10 is 0.1, but then 1 over 1,000 is 0.0001. 1 over a million is even smaller than that, and if you think about it, 1 over infinity is essentially just 0. If you have any constant, does not matter, 3 over x, the result will still be the same. You can think about it as 3 times the limit as x approaches infinity of 1 over x. This component is 0, so 3 times 0 is going to be 0. So it does not matter what constant you put up there, and it does not matter what constant you put on the bottom. If you have 1 over x plus 2, or we can do 3 over x plus 2, it really does not matter. Any terms that are like added onto the x that are not connected to the x are invalidated when it goes to infinity. You can think about it like this. The limit as x approaches infinity of x is just infinity. Of x plus 2, it's infinity plus 2, but you can't get bigger than infinity, so infinity plus 2 is still infinity. It's not a bigger infinity. Infinity just means infinite. However, it doesn't have to approach 0 in every case. You can have a function like 1 over x plus 2. This plus 2 is not connected to the x. It's not added to the x, it's added separately of the x term. So as x approaches infinity, we know this goes to 0. However, this 2 has nothing to do with the x. So as x goes to infinity of this part is 0, this part stays as 2, so 0 plus 2 is going to be 2. And this is also going to be the horizontal asymptote of the function. The horizontal asymptote is the limit as x approaches infinity and the limit as x approaches negative infinity. So, for instance, if you have the function 2x over square root x squared, if you want to find the horizontal asymptotes of this function, well, let's look at it. Limit as the x approaches infinity, all right? We're going to have 2 times infinity over the square root of infinity squared. But since this square root can cancel with this square, you have 2 times infinity over infinity. And these infinities can cancel out. So this is 2. The limit as this approaches infinity is 2, which means that the horizontal asymptote, or at least one of them, because we want to find both, is 2. So we know on a graph that one of the asymptotes, however it is, however the function is, will end up at 2. Now let's look at the other side. Let's look at negative infinity. 2 times negative infinity over square root negative infinity squared. Negative infinity squared, you can get rid of the negative because negative times negative is positive. So negative infinity squared is still just infinity squared, and we can get rid of the square root like we did before. So we have negative 2 times infinity over infinity. Now we see that it's negative 2. So the horizontal asymptote, as we go left infinitely, is going to be whatever graph, and then eventually it will settle on the value negative 2. Finally, we can get some coefficients involved on top and on the bottom. So if we have 2x plus 1 over x minus 3, we take the limit as it approaches infinity. We're just going to look at infinity here. Because, like I said before, this 2x plus 1 term is incorporated into the whole x term. Same with this x minus 3. If I added a plus 2 over here, this term is separate from this whole term right here. So that plus 2 would not be affected by the infinity. But here, the plus 1, the negative 3, essentially just get canceled out. And then you have 2x over x, right? As it approaches infinity, it's just going to be 2. And that is the rule for any limit as it goes to infinity of 2 coefficients. If you have the limit as it approaches infinity of ax over bx, it is going to be a over b. So if you have 3x, well, I should add in the rule, plus c and plus d. So if you have ax plus c and then bx plus d, is just going to be a over b. So if you have 3x minus 1 over 2x plus 4, you can use this rule and conclude that this limit is just going to be 3 over 2. And you can mess around with this in a graphing calculator to see it's always going to work out this way. And if it ever asks you to find something like horizontal asymptotes, you just got to know that you take the limit as it goes to infinity. The final topic is intermediate value theorem. So this is probably the easiest topic in the whole unit. Intermediate value theorem, also known as IVT, which is what I'm going to call it because intermediate value theorem is a mouthful. So IVT. IVT essentially states that if you have a continuous function, has to be continuous, between a and b, that was a bad a that I chose for this problem. But if you have a function that's continuous between a and b, then the function must hit all values between f of a and f of b. So all that's saying is that if you start at point A and end at point B, and you have a continuous function, it doesn't matter what route you take to get there. As long as it's continuous, it has to hit all values between a and b. It can go to other values, but it must hit all values between a and b, or between f of a and f of b. So if you have a function that starts at -2, -2, and then goes to 3, 2, however which way it gets there, you can guarantee that since it's between -2 and 2, the function will always hit the value 0. It will always hit the value 1. It will always hit -1. It will always hit 1.5. Any value between -2 and 2 it will hit, as long as it's on the interval between x is greater than -2 and x is less than 3. So, how you write that formally on the AP test is, since f of x, or whatever function you have, is continuous on the interval a to b, then, or you can say there, must, keyword must, be a value, you can just say there must be value c where a is less than c, which is less than b. So it's saying the x value c is between the x values a and b. And f of a is less than f of c is less than f of b. This is how you formally write it. You can plug in the values for the FRQ if it says it's between 1 and 5, 2 and 8, whatever it is. You write it like this, you will get full credit. Or if you write it any way that includes these main parts. Continuous on A to B. The word must be, and then in some capacity you say the x values between the interval, and then the y values are between the first and last y value of the interval. This is the theorem. Conceptually, just means that it hits all the y values on a continuous function, and it is very common on the test. You will be asked at least one question about it, whether it's a multiple choice or whether it's a part on an FRQ. You need to know this theorem. So the theorems and the rules you need to know how limits work mainly graphically. Algebraically and from a table are less common, but they can appear. But this is important, how they work graphically. You need to know limits as x approaches infinity, because this does come up later, multiple times in different units. And you need to know IVT, and finally prove continuity. These are the main things you need to know. Rewatch the video if you missed any one of these main points. The other stuff is important, but these 4 things will always show up in some capacity on the test. So, that is it for limits and continuity. And I will see you in the next video. Thanks for watching.